Hello everyone, we're presenting our final project for social networks, a predictive modeling of professional tie formation. We set out to model how professional ties form on platforms like LinkedIn. Since LinkedIn's graph is private and locked behind API restrictions, we use Facebook Ego Network as a structural stand-in because both platforms follow the same mutual connection logic. We combine a stochastic actor-oriented model with classic proximity heuristics to find out which dormant connections are most likely to activate next, or headline finding. Triadic closure, simply having mutual connections, is the strongest predictor of new professional ties. That's essentially the logic behind people you may know style recommendations. This matters because network structure shapes career trajectories and information flow. Since we couldn't access LinkedIn directly, we needed a proxy that preserved the same underlying structure. And the Facebook Ego Network gave us that. Our end deliverable was a ranked forecast of which professional pairs are most likely to connect next. Why does Facebook work as a stand-in? Both platforms are built on undirected mutual connections profiles map to profiles, friendships map to connections, shared friends map to mutual contacts, and friend groups map to professional circles. The structural translation holds up well. To validate our prediction, we needed a ground truth. So we built a two-wave setup. The first wave simulates the past by randomly removing a portion of the observed connections. The second wave represents fully observed state. The task was to predict which missing connection from the past reappear in the present. Looking at the overall structure, the network is quite sparse. People connect with only a small fraction of others, but clustering is high, meaning if two people share a connection, they're likely connected to each other too. Most people have just a few connections with a small number of much more connected actors. We tested a few baseline heuristics for predicting new links, and the one that weights shared connections more heavily, favoring rare, specialized mutual contacts over generic popular ones, perform best. Simply relying on raw popularity perform noticeably worse, reinforcing that shared context matters more than general visibility. That covers our setup, our proxy justification, and our baseline approach to link prediction. Setting up to more advanced modeling we get into next.
Moving in a macro level structure of a network, we applied community detection algorithms to understand how the graph naturally segments. From this analysis, six distinct professional circles emerge. Our model recorded a modularity score of 0.4197. In network science, a score above zero point 0.3 confirms robust community structure, meaning we are looking at mathematically distinct groups, not just a random configuration. The variance in the sizes of these communities perfectly mirrors reality. We observe one large network, typical of a current employer, existing alongside smaller, more tightly knit circles that might represent past institutions or specific project teams. We also analyze structural holes. We identified specific nodes with maximal betweenness centrality. These individuals act as vital bridges between these different communities, strategically controlling the flow of cross industry information. Understanding these communities is crucial when we examine how information actually spreads. To model this, we looked at influence maximization using the independent cascade model with a transmission probability of 0.05. The objective was to find the optimal starting points or seed nodes to disseminate information across a network. We use a greedy approximation algorithm to select our top 5 seed nodes because the spread of information in this context is submodular. This greedy approach mathematically guarantees a solution that is within at least 63% or 1 minus 1 over E of the absolute theoretical optimum. When we compare this strategic approach to a baseline of simply picking the most popular people, the results clearly show that the greedy algorithm beats naive popularity. Our greedy selection yielded an expected spread of 100 compared to 96 from the degree of centrality baseline. That represents a 4.2% increase in total reach. This happens because the greedy algorithm explicitly penalizes overlapping spheres of influence instead of clustering our seed nodes in the dense core of the network, where they would just reach the same mutual contacts. It strategically spreads them across the discrete professional circles we identified earlier. The practical takeaway for scenarios like recruitment or product announcements is significant. Targeting five well distributed professionals across different communities will consistently outperform targeting the five individuals with the highest absolute connection counts. Beyond mapping current influence, we wanted to accurately forecast future connections. To achieve this, we implemented a stochastic anchor oriented model, or SAOM. Unlike the baseline single metric heuristics, the SAOM allows us to evaluate the simultaneous interplay of multiple structural forces using a logistic regression formulation. Specifically, we evaluated four key factors. First, density, which is the baseline cost of forming any random tie. Second, transitivity, the strength of mutual connection effects. Number three, preferential attachment, which is the pull of already well connected actors. And in the last order, number four, is JWESP, which models the diminishing returns on shared partners. Our maximum likelihood estimates reveal exactly how these forces drive tie formation. First, density is strongly negative at minus 2.38. This confirms that professional networking is highly selective. People do not connect at random. Second, shared partners or transitivity shows a positive effect, proving that mutual ties are our primary driver of new connections. Third, preferential attachment or raw popularity has only a marginal positive pull. Finally, GWESP demonstrates a strong positive but saturating effect. GWESP is critical because it captures diminishing marginal utility. Having one shared contact dramatically raises the odds of two people connecting, but mathematically, the difference between having five mutual contacts versus six is negligible. To validate this model, we tested it against withheld ground truth data. We ran 500 Monte Carlo simulations, predicting the 15% of edges we had intentionally removed to simulate a wave 1 bias state. The SAOM achieved an impressive AUC ROC score of 0.9405. This integrated formulation outperformed every single metric heuristic we tested. It empirically proves that capturing the nuances of professional tie formation requires a combination of density, transitivity, preferential attachment, and GWESP. To ensure the integrity of these findings, our system architecture was designed as a fully reproducible computational pipeline. The repository is organized as follows: a data directory for a raw edge list and temporal splits, an analysis directory containing the Python scripts for link prediction, community detection, and the SAOM, a front-end dashboard built with Vue.js3, Vite, and v3.js for force-directed network visualization, and a results directory storing structured JSON outputs. The entire workflow, from graph building to a maximum likelihood estimation, is orchestrated automatically by a single run all.py Python script. And finally, to conclude, our analysis of professional networking demonstrates that structure inherently predicts connection. And we leave here with three final takeaways. First, the proxy holds up. Facebook Eco networks proved to be an excellent structural proxy, successfully reproducing the scale-free, high clustering, and modular nature of LinkedIn's graph. Second, triadic closure dominates. Mutual connections, not raw popularity, are the overwhelming driver of new professional ties. Third, bridges matter strategically. Effective networking depends heavily on connecting distinct highly clustered circles rather than just accumulating connections. Ultimately, our AUC ROC score of 0.9405 provides robust empirical validation for the theoretical logic behind modern algorithmic friend recommendation systems. And that's it. That's pretty much all about our project.